Alright, a fun little problem where we're doing conservation of energy with gravity and a spring together. This is the real deal here. This is number 33 for chapter 8. So, just redraw the diagram real quick. We got a, nope, stop. We got a ramp going up, and at the top of the ramp we got a spring hanging down with a little platform, and we got the ramp's at an angle of theta, and the distance is d from here to the relaxed spring. We got a mass that's pushed up, if I remember right, pushed up into it for a certain distance. So mass is pushed up into the spring a certain distance, delta x we'll say, and the spring has a spring constant k. So those givens are k equals 170 newtons per meter, theta is 37 degrees, d is 1 meter, m is 2 kilograms. I don't know what accent this is. This delta x is 0.2 meters. Yeah, part A. Part A. What is the speed of the canister at the instant the spring returns to its relaxed length, or right when it loses contact? So we push the mass up, 0.2 meters, 20 centimeters up into the spring. Let it stay there at rest, then let go, and the spring pushes back. As soon as the spring is relaxed, and we'll assume that the mass loses contact with the spring at that point, then we want to know that speed. So, conservation energy, mechanical energy initial. That's bad. That's bad. um, yeah, whatever. So mechanical energy initial is going to equal mechanical energy final. And what individual energies make up the mechanical energy initial? Well, we got the kinetic energy initial. We got some gravitational potential energy, UG initial. And we got some spring potential energy initial. And then we also have some of that final. Alright. Now some of these are zero. For example, when the block is initially up, pushed into here, x, it's at rest, so that's gone. And once it's reached the relaxed state of the spring, it's no longer touching the spring, so there's no more spring potential. And you know what? Let's define this position for this part, for part A anyway, as the lowest it can go gravitationally. And so we'll call this 0. We can do that, you know? We can do that. So now this becomes mg h, where h is going to be the vertical height that it drops. So let's draw a little triangle real quick. We know that the hypotenuse is delta x. That's the distance it goes along the ramp. We know it drops a vertical height h. And we know this angle here is the same angle as the ramp, and that's 37 degrees. It's h. So h is going to equal, SOHCAHTOA, h equals delta x is 0.2 sine 37, right? 0.2 sine 37. And so plus 1/2 k delta x squared. And that's going to equal kinetic energy final 1/2 mv final squared. So let's just plug in here. Well, actually, we could solve this. This is 0.12 meters. Yeah, so let's plug stuff in. Mass is 2, so 2, 9.8, 2 times 0.12. That's the height that it vertically drops while it's being pushed out by the spring. Plus 1/2. K is 170. Delta X is 0.2 squared. That's going to equal 1/2. Mass is 2. Velocity final squared. Solve for velocity final. A little bit of algebraics here. And that's going to equal 2.4 meters per second. So that was cool. Now part B is asking, what is the speed of the canister when it reaches the lowest part of the incline down here? Well, we could go from here to here, and that way we wouldn't have to deal with spring anymore. So let's do that. So we got mechanical energy initial, which is now here, not the same as up here. So if you're watching this video and not really listening, you might get confused. Don't get confused. I could put 1, 1, 2, 2 here, but I'm not gonna. Anyway, so this is just kinetic energy initial plus gravitational initial, and no spring because we're going to go from right when it leaves the spring to the bottom, basically just from here to here, D. KE final plus UG final, and this is 1/2 MV initial squared plus mg h2, where h2, we're going to do the same triangle thing. H2 is here, the vertical distance. D is the hypotenuse, so we're making a triangle out of this, basically. And we know the angle here is still 37. And so H2 is D, which is 1, times sine 37, which equals 0.602 meters. So we'll stick that in there eventually. And that's 1/2 mv final squared plus 0. We'll say that 0 because we'll define the lowest gravitational potential energy to be here at 0. To be 0 here. Alright, 1/2, 2. We know that speed because we got it from part A. 2.4 squared, so that's the speed right here. Without that speed, we couldn't do part B this way. We could do it from here to here, which is another way. You might want to challenge yourself, and instead of doing part B using the speed from part A, basically set it up just like this. But now the H here is going to be this H plus H2. That's my hint for you. So maybe call it H3. Anyway, plus 2 times 9.8 times 0.602, and that equals 1/2 times 2 times velocity final squared. In this case, velocity final should be faster, right? Because it's going down the ramp even more, and it is. It's 4.19 meters per second. Yeah. All right, and that's problem 33. That was a cool one.